All right. Hi, everybody. Julie, which one can you see? Is it the wrong
The
one?
Yeah, the wrong one.
It's the wrong one. Okay.
Do the display settings and swap them there.
Okay. Does that look better?
Yep.
Great. Cool. Well, hi, everybody. Um, and now I can't see how many people are in, but that's okay. Folks are coming in. I'm going to go ahead and get us started here so we can move on to the main presentation. So, all right. So good evening, everyone. My name is Kellen Damon. I work with the County Marin on the sustainability team. We are part of the Community Development Agency. I'm joined tonight by Julie Chu, who's our media tech, Sarah Thatcher, who's program coordinator with us and Electrify Marin, and Russ King, who's going to be giving the presentation. So I just have a couple intro slides for you. I'm going to keep this brief. First, I'm going to pass it off to Julie to do our webinar housekeeping. Oh, you're muted.
Rookie
Thanks, Kellen.
mistake.
So for tonight's agenda, our main presentation will be running from about 6 p.m. to 7 p.m. Then we will have some time afterwards for a Q&A. If you have any questions, please enter them into the Q&A box. You can upvote questions from other attendees. All attendee mics and cameras will remain off for the duration of the session. Use the chat box for general comments. The live transcript and closed captioning is available, and you can enable it by clicking on the CC icon. The video will be recorded, and slides and other materials, and the link to the recording will be sent via email, and we'll also make all the materials available on our website in the future. And now I'll turn it back to Kellen.
Awesome. Thanks, Julie. So we are part of the sustainability team with the County Marin. I'm not going to read our mission statement, but we have a great website and we're on social media where we post events like this. We also have an event page and a newsletter that you can sign up for if you want to be kept abreast of everything going on with us and future educational opportunities like this. One thing I want to point out on our website is the electrification hub. So we put a bit of work into this to make all the resources available for folks that are looking to electrify their homes. So changing your furnace to a heat pump, water heating to a heat pump water heater, your cooking to induction cooking. We have a lot of resources on that. And I'll just go through these quickly. Current information on incentive programs. There's a bit of news around that. So the statewide program just ran out of funding, and the Inflation Reduction Act HERA program was put on pause because of executive orders and all that stuff that you've probably been hearing about in the news. It is put on pause. It's, I can't say what's going to happen with it. Nobody really knows. But we will be keeping our finger on the pulse there and updating our resources and also sending out information to folks as we learn about it. Another thing on there you can check out is the Rewiring America tool. They have information on tax incentives for heat pump projects as well as solar battery energy efficiency projects that you do to your home. Those are still available as far as I know as of now. Energy audit and concierge services. We have information on that. I do just want to highlight those briefly, especially for folks that are looking into heat pump projects. There are these private concierge services that are there to kind of walk people through the process, see if your home is ready for installing a heat pump, space heater, and also looking for rebates and help you, fill out the paperwork and that sort of thing. These are third-party independent companies, so we don't really, endorse them. We don't work with them. This list is just for informational purposes, but we do have links and information on those services on our website that I'm going to be sending out to everybody. Home energy score is also a great way to get started. You have someone come out to your house and they give you a whole energy efficiency assessment, including an electrification checklist. And there's a $200 rebate for every home score done in the Bay Area, including Marin. And then there's a low-level greenhouse calls where they basically send you an energy efficiency kit that has LED light bulbs, low flow faucet aerators, smart power strips, and that sort of thing. Just a brief home energy 101. So we really like to stress in the messaging in our department just to focus on efficiency first. I know that Russ has a little bit on this of, that our biggest energy resource is the energy that we waste. And especially when you're considering HVAC, so, how you heat and cool your home, making sure that the money that you're paying to heat and cool the air that's getting into your house is not escaping into your attic and crawl space. So making sure you have great air sealing in the house, and also insulation will help make sure that your furnace and HVAC system is running smoothly and needs less maintenance and that sort of thing. I already touched on these. Some additional resources that I'll include in the follow-up slides on induction cooking, solar and battery, and fire-safe Marin, because it's always important to make sure that your home is better prepared for wildfires. I will include that. At the end of this, I'm going to be sending out a link for a survey. This just helps us make improvements to these webinars. We take suggestions on topic ideas and that sort of thing. We're going to be raffling off, a handful of solar and battery phone chargers to folks who respond to the survey, just as a little incentive. And yeah, I'll send out that link in the chat and also in the follow-up material. So without further ado, let's kick it off to Russ King. Russ King has been doing these classes with us for a while now, and he's been working with our department to help educate our Marin City and Town building departments on the Title 24 code of the building code, which is the energy code. So he's a great expert, and we're super lucky to have him talk about heat pumps for space heating tonight. So take it away, Russ.
Awesome. Thanks, Kellen. Good evening, everyone. Thank you for joining us this evening. It's nice to be here to be able to bring this presentation to you, this good information. We appreciate you taking some time out of your busy day, your busy evenings, to learn more about heat pumps. So if you were here last week on Wednesday and sat through the heat pump for water heating class, there's going to be a few slides that are repeated from that when we start talking about sort of the basics of heat pumps and stuff like that. But that's okay. It's never a bad thing to refresh your memory on some of those things, and I'm sure a lot of that didn't stick the first time through, so it'll be good the second time through. But for those of you who did not, welcome, and hopefully you'll learn something. So we're going to talk about we'll do a little bit of introduction. We're going to talk about some terminology to really understand heat pumps. Unfortunately, you have to learn a little bit about thermodynamics in order to understand them, and so I'll try to make it as painless as possible. We're going to talk about some super basic thermodynamics and the refrigeration cycle and how it works. And then we're going to talk about the advantages for heat pumps for space heating. And we're fair. We'll cover the disadvantages as well. And then we're going to talk about the different types of heat pumps. And then we're going to talk about the importance of properly sizing heat pumps. And then at the very end, we'll have some time for questions and answers. All right, so introductions. Well, let me introduce myself first. I'm a licensed mechanical engineer in 3 states. I've been doing HVAC design for a long time. When I first started doing design, there wasn't even software to do it. There was these pre-printed worksheets that you had to fill out by hand, and it was a lot of work. My company right now is called Coded Energy Inc. We're the developers of a software called Quick Model 3D. And we also have a website called DIYLoadCalcs.com, where we help homeowners do load calcs on their own home. There's my email address. I do have a blog, russellking.me, where I talk a lot about HVAC kind of stuff. And I wrote a book, HVAC 1.0, an introduction to residential HVAC systems that's used in some community colleges and trade schools as a textbook for very, very basic HVAC classes. So, all right, let's see here. So, to really appreciate heat pumps, you first must understand a little bit about how and why we heat and cool our homes. Okay. So, clearly, the main reason is for comfort, right? But in some climates, it's considered a health and safety issue. All right. Even in a lot of California, it gets very, very serious when we have very high heat waves, and it can be dangerous. All right. So, but the point is that we live in this bubble, okay, that we call a house, and this bubble is an envelope, and this envelope has surfaces on it. And when it's really hot outside, the heat's trying to get in. All right. And we'll talk a little bit about heat. It's BTUs. So the BTUs are all on the outside. There's more of them on the outside, and they want to come into the house. Okay. And if we just let them do that and didn't fight it, the house would eventually reach the same temperature as outside. So let's say it's 90 degrees outside, okay, and it's a nice cool 75 degrees inside the house. And if we just left it like that without any mechanical equipment or anything, eventually it would get to be 90 degrees inside the house. And that's what we don't want. We want to keep it at 75. And one of the ways that we help prevent that from happening is we make a really nice envelope. We try to reduce the amount of heat that's coming in by having really well insulated walls, by having a really well sealed envelope, having shading devices on our windows and shade structures and trees and things like that. So we keep the BTUs from coming in at first, but we can't stop them. It's impossible to stop the BTUs from coming in. All we can do is throw them out as fast as they come in. And so the BTUs are going to come in at a certain rate, and we need to remove them at least the same rate in order for our house to stay comfortable, is to stay cool on a hot day. And then in the winter, the exact opposite is true. All the BTUs are inside the house, and because they're more dense inside the house, they're trying to escape to the outside where it's cold. So let's say the inside of the house is 70 degrees and the outside is 20. The BTUs are all trying to escape. All right. And they are escaping. And we reduce that as much as we can by having a really efficient envelope. All right. And we need to replace those BTUs as fast as they're escaping if we want to maintain a comfortable temperature. Okay. And we can calculate how fast those BTUs are escaping when it's a certain temperature outside. And we can calculate how fast the BTUs are coming in when it's a certain temperature outside. That's called a load calculation. All right. Um, but and it's very easy to replace BTUs. Okay. It's very easy to heat a house. You can burn all your newspaper in the middle of your room and heat your house. All right. There's a lot of places to get BTUs from. But because of the impacts of energy use and where it comes from and how it's used, we're trying to do that as efficiently as possible using using an energy source that's as clean as possible. Okay. So those are our goals. Our goals are to keep our house comfortable, but do it in a way that's good, that's environmentally conscious and reliable, of course. All right. So, first of all, HVAC stands for heating, ventilation, and air conditioning. The main goal of an HVAC system is to maintain a constant temperature in a house. Houses lose heat in the winter and they gain heat in the summer. To maintain a constant temperature in the house, the heater must replace the BTUs that are escaping, and the air conditioner must remove BTUs that come into a house. All right. So when we cool a house, when we cool a house, we don't put coldness into a house. It seems like we do. It seems like we put coldness into a house. We're blowing cold air into the house. So it seems like we're putting coldness into the house, but we're not. What we're really doing is we're removing BTUs. So you have to think of everything in terms of BTUs, little units of heat that are going Think of them as they're antisocial. They don't like each other. And so wherever there's a lot of BTUs, they want to get away from each other. So they're going to where there's less of them. All right. So so that's what it's all about. We're going to keep that in mind. It's all about moving heat from one place to another. Okay. So just some real basic terminology. What exactly is a BTU? All right. Well, it's a unit of heat. To quantify it, it's about the same amount of energy that's stored in a wooden kitchen match. All right. If you take a wooden kitchen match, you strike it and you let it burn all the way down and you throw it down, you've just released 1 BTU of heat into the air. So we quantify heat movement as a rate. It's BTUs per hour. How many BTUs per hour are going from here to here? All right. And that's how we rate equipment. Air conditioners are rated in BTUs per hour, and furnaces and heat pumps and everything else are rated in BTUs per hour. And so when you think about a 2-ton air conditioner, and by the way, tons is an old term. It has nothing to do with the weight of the equipment. It has to do with how much heat is stored in a ton of ice. All right. And it turns out it's about 12,000 BTUs per hour. Or how many BTUs per hour does it take to melt a ton of ice? Put it that way. It's about 12,000 BTUs per hour. So a 2-ton nominal 2-ton air conditioner is 24,000 BTUs per hour. It can remove 24,000 kitchen matches worth of heat in 1 hour from a house. Okay, so hopefully that kind of quantifies it for you. Kind of helps you think about it. So we're going to represent BTUs as these little flying kitchen matches, okay, to help you. Oh, and I do have a slide on tons. I forgot about that. Before mechanical refrigeration, the way they cooled food and things like that is the trains would go up to Truckee and cut ice out of the lakes and bring the ice down to the city, to the Bay Area, to San Francisco, and they would take these giant blocks of ice and they would buy them by the ton. All right. And they would use this block of ice to cool their vegetables or their fish or whatever they had. And it turned out that a ton of ice, well, someone started marketing this mechanical refrigeration. And they said, hey, this device right here will do the same thing as 2 tons of ice, or it'll do the same thing as 4 tons of ice. And it'll keep your stuff cool, but you don't have to keep buying the ice. All right. That's the great thing about it. Well, it turns out that an ice is worth about 12,000 BTUs per hour. And so that name just kind of carried over to equipment. So they call it, you'll hear the expression, a 2-ton air conditioner or a 3-ton air conditioner or a 5-ton heat pump or, stuff like that. So that's where that comes from. But it's important to understand that that's what we call the nominal capacity. When a manufacturer builds an air conditioner, they shoot for a certain level, and they're shooting for around, let's say, 24,000 BTUs of cooling. And if it's close, then they say, okay, that's our 2-ton unit. The actual capacity, the actual installed capacity, depends on a lot of things. How much cooling you're really going to get out of that air conditioner depends on a lot of things. It depends on how hot it is outside, how humid it is inside, how much airflow is passing across the coil, and things like that. So there's a lot of things that affects that. So just because something is called a 2-ton, don't assume that it gives you a certain amount of cooling. You have to do some calculations and see how it's going to adjust. Just an example, a 3-ton air conditioner that's installed in, let's say, Sausalito, okay? They don't need a whole lot of air conditioning there, but if they put in a 3-ton air conditioner in Sausalito, that exact same 3-ton air conditioner, if you put it in Las Vegas, won't give you the same amount of cooling. It's the exact same air conditioner, but the reason it won't is because it's taking air and is trying to dump it to a much hotter outside temperature. So the design temperature in Sausalito is probably like 85 or 88. The design temperature in Las Vegas is like 110. So to move air from a house to 110 degrees is a lot harder to do. So the air conditioners have to work harder and it won't give you as much air conditioning. All right. So that's an important concept, is don't just assume that they have a certain amount of cooling. The cooling load of a house is defined as how many BTUs are coming into the house per hour under certain design conditions. Okay. So you look at the house, you look at all the surfaces, the areas, the windows, what direction they're facing, what kind of insulation, how leaky is the house. And you can calculate on a design day how many BTUs are coming into the house. And what that does is it allows you to size the equipment to meet that requirement to keep your house cool. Because remember, we want to remove the heat as fast at the same rate or slightly more than it's coming in. Okay. The cooling is a process of removing heat, as I said. Consider an air conditioner that has 24,000 BTUs. That's 24,000 kitchen matches worth of heat per hour that it's pulling out. A 2-ton air conditioner is not very big. All right, the 2-ton air conditioner is not very big. Out here, and I live out towards the Central Valley, and it's quite warm out here. And you'll see 2,000 square foot homes out here, or 2,500 square foot homes that have 5-ton air conditioners in them. All right. But that's way oversized, but they just didn't know any better back then. We'll talk a little bit more about that. All right. Now then heating is the opposite. So in the winter, the heat is escaping. All right. And the heating load of the house can be calculated. You can look at all the surface areas, and most of the heat loss that we have is either through conduction, which is the heat passing through the walls, or it's through infiltration, convection, which is heat escaping by leaky air. All right, that's where most of the heat load is. By the way, on the air conditioning side, you have those, but you also have solar gains. So the sun is shining on and bringing BTUs into the house in the form of sunlight. All right, so cooling load calculations are a little more complicated than heating load calculations. But anyways, the point is you can calculate that. All right, you can make some estimations about some things, or you can actually measure them. And then that number is very, very important. Okay, that load number. That's like your dress size or your tuxedo size. Okay, I use that example a lot. Let's say somebody called you up and says, "Hey, I need a tuxedo. Will you go to the store and rent one for me right now?" And you're like, "Well, how big are you? How what are your measurements?" Just go get me one. Well, if you have no idea how big this person is, you've never met him, you've never seen him, what are you going to do? How are you going to pick a tuxedo for that person? And the human nature is to guess big, right? So at least they can get into it instead of being all too tight. The same sort of thing happens with air conditioners and heaters. Contractors do not do load calculations like they should. Some of them do, but not many. And so they're guessing. They're guessing on how big of an air conditioner or heater your house needs. And it's human nature to say, well, I have no idea, so I'm going to guess big. At least I know it's going to cover the loads. But what they don't realize is oversizing the equipment can actually cause more complaints, more problems than if you were to undersize it. Okay. So it's different than a tuxedo. If you put on a tuxedo that's too big for you, at least you can move around. But if you put on a tuxedo that's way too small for you, you look kind of silly and you have trouble moving around. But with air conditioners, if your air conditioner is a little bit too small, it'll still work fine the vast majority of the time. It'll only not work as well on the really, really hot days. Okay. And if you oversize it, it's going to cause all kinds of problems. And we'll talk about those. Okay. So heating is a process of adding BTUs to a house, okay, to replace the BTUs that are lost. So the same sort of thing. You'll see gas furnaces out there. 30,000 BTU furnace is a small furnace. They go up to 120,000 BTU furnaces are not uncommon. So that's 120,000 kitchen matches that you'd have to light in an hour to meet that requirement, okay, to have the same sort of heat input. Okay, so to maintain a constant temperature, the heat coming in has to equal the heat that's leaving. Okay, so you can calculate that number, that amount of heat that's leaving, so that you can size your heater to to replace those BTUs. You can calculate the amount of heat that's coming in the summertime, so you can size your air conditioner, remove those BTUs. Okay, so pretty straightforward. All right, so we're going to talk about the equipment now. The equipment has a capacity. The capacity is sometimes called the output. So it's how much heating and cooling the equipment gives you. Think of that as the supply. All right. The load of the house is what the house needs. It's the cooling demand. It's the heating demand. Think of that as the demand. So you've got supply and you've got demand. The equipment provides heating and cooling. The house needs it. All right. Sizing equipment is the art, the art of matching those two things together. Okay. But it's also really, really important to understand that you can control both of those things. You can control the load of your house almost more easily than you can control the equipment capacity. Okay. And what I mean by that is if you have the opportunity, if you're thinking about putting a new heating system or air conditioning system on your house, is you really should first look at your house and say, what can I do to reduce the load of my house? It's always, always more cost effective to reduce the load of your house first. Okay. And it's a win-win situation. All right. And I teach a lot of HVAC design classes. And I tell people in the class, one of the things I just throw out there to kind of get them talking is I say, don't you ever design an HVAC system for a crappy house. And like, well, what do you mean by that? That's an odd thing to say. Why can't I? If I wanted to, I could, and I say, no, what I'm saying is if you have a house with no ceiling insulation in it, would you put that in your load calculations? Would you say, I'm going to size my equipment assuming that house has no ceiling insulation? That's not a very smart thing to do. You should put ceiling insulation in that house. It'll reduce your loads, okay? And you can have smaller equipment and the house will be more comfortable and you'll use less energy. It's a win-win situation. All right. If somebody asked me, I could probably design a heating and cooling system for a house that's made out of chicken wire. All right. Chicken wire and plastic bags. All right. That's all it is. I could design an HVAC system that'll make the inside of that house the right temperature. It won't be comfortable. It'll be very drafty. All right. But it'll keep it at a constant temperature and it'll be much larger than it needs to be. So what should you do is, well, don't live in a house made out of chicken wire. Live in a house that has insulation in the walls. And there's a lot of houses in the Bay Area that what we call the low hanging fruit. There's some really great opportunities to save a lot of energy without spending a whole lot of money. And you will definitely recover that money in the savings by having a smaller, better performing heating and cooling system. Okay. So I'll mention that several times throughout the presentation. So good equipment sizing is the ability to match the equipment size to the house's demand. And both of those you can change. One of the problems that I run into a lot with HVAC contractors is they don't even think about changing the load of the house. They're only concerned about the equipment. If a homeowner calls them up and says, you know what, my house, it just won't stay warm in the wintertime. What's the contractor going to say? Well, let's put in a bigger furnace. Right? When you're a hammer, everything looks like a nail. All right. When you're an HVAC contractor, everything looks like an HVAC problem with an HVAC solution. That is not true. All right. You need to be able to look at the house and say, I can do something about that house. And maybe that's all I have to do is just insulate and seal the house. And then maybe the load will come down to match the capacity of the equipment. All right. And you'll be better off. Okay. Important to understand that. Okay. So undersizing is when the capacity of the equipment cannot keep up with the house. Undersizing, the equipment will not put out enough heating and cooling to keep up with the load. And so the house potentially doesn't heat or cool when you want it to. All right. But, well, I'll get to this in a second. Okay. Oversizing is the opposite. Oversizing is when the equipment has way more capacity than the load of the house. The supply is much greater than the demand. That can cause problems. All right. So when we size equipment, we assume certain conditions. We assume certain indoor conditions, temperatures, and we assume certain outdoor conditions, temperatures. We're very fortunate we live in a dry climate. Okay. We don't have to worry about humidity that much. So these design conditions that I'm talking about are established by code. Code tells you what you're supposed to use. These code specified indoor and outdoor temperatures are what we use to calculate these loads. Okay. And as an example, what do we got here? We got, there's Sebastopol, Scotts Valley, that's over towards Santa Cruz, Scotia, that's up the coast a little ways. The cooling outdoor temperature is what's called the 1% design temperature. And here's some example numbers here. You've got Selma, which is, I think that's down towards Fresno, 100 degrees. Sepulveda is 96 degrees. Seaside over towards Monterey is only 77 degrees. Seal Beach, 84, Scotts Valley, 86, Scotia, 73. Those are outdoor design temperatures, okay? In California, the indoor design temperature is 75. So we pick our indoor temperature, we pick our outdoor temperature. That gives us something called the delta T. We size our equipment for that delta T. It's only that delta T, not very often, okay? Only 1% of the time is it higher than that delta T for cooling, all right? So the point is, if you were to graph temperature throughout the day, it's a big bell curve. It starts off cool, gets hot, and goes back down. The vast majority of the time, it's below the design temperature. So when you undersize an air conditioner, it's going to work for most of the time. It will be perfectly okay. But if you oversize an air conditioner, it's going to be oversized all of the time. And on the milder times, it's going to be way oversized. And that makes problems. Okay. So the indoor winter indoor temperature is 68 in California. The summer indoor temperature is 75. Don't stress out about those numbers. Those are just the numbers we use to do some calculations. Okay. Don't think that if I size my air conditioner to or my heater for 68, it's never going to get above 68. That is not true. Okay. And by the way, the load calculations that we do uses a methodology called Manual J. Manual J, if anything, is safe. There's actually people out there that saying it estimates way too high on the load calculations. So it is safe. Okay. And then the winter outdoor temperature in California, we use something called the winter median of extremes, which is actually a lot more extreme than what the rest of the country uses. The rest of the country uses a 1 percentile. We use something called the winter median of extremes to size our stuff. Now, it absolutely does get colder than that. It absolutely does get warmer than the outdoor summer design temperature. But houses have something called thermal mass. Okay. If the outdoor temperature right now, as we're sitting here, if the outdoor temperature was to rise up 20 degrees for 15 minutes and drop back down, would we even notice it? Probably not. We probably would never even know that happened outside. It's a very weird thing to happen, but we would notice it. Okay. People outside would, but people inside the house would. And the reason is that there's a buffer. The house is a buffer. So even though we design to a certain temperature and it might get hotter than that, it only gets hotter than that for a short period of time. And your house has the ability to buffer you from that change. Okay. Let's see. Got a question here. Can you point out that the code does not take climate change into account yet? Not really. Every now and these temperatures here come from a document that's actually by NOAA, NOAA, the National Oceanographic and Atmospheric Administration. And it's statistical data. Every now and then they update these. So they do update it to include more recent data. And yes, the numbers are going up, but it would have to go up a lot for it to make a big difference. Okay. Equipment only comes in certain sizes, and the sizes are big jumps in between. Okay. And even if the average temperature on planet Earth goes up by a couple of degrees, which is a lot for it to go up by, we probably wouldn't notice it in our homes. Okay. What will happen is that it will stay hot for longer periods of time. The extremes will get hotter, but I think what will be more noticeable is that we'll have more hot days, not so much really hot days. Okay. But we'll have those too, I'm sure. But anyways, I wouldn't worry too much about that. In terms of designing your air conditioning system, I would worry about it a lot for other stuff. Okay. That sounded terrible. Okay. The system needs to also work at milder conditions, and it's milder most of the time. Okay. If we design to really bad conditions, we will be oversized for most of the season. Oversizing causes more comfort complaints, the biggest of which is something called short cycling. All right. And what that means is you set your thermostat to a certain temperature. Let's say we're in the summertime and you set it to 75 degrees. And it starts to creep up past 75 degrees. And as soon as it gets above 75 degrees, your air conditioner goes, hey, it's getting hot. Let's turn the AC on. So the AC turns on, but if it's oversized, it's going to blow really cold air. Okay. Oversized equipment blows colder air than properly sized equipment. And then it blows a lot more of it. So it's like, oh, I use the analogy of I worked 2 summers on a salmon boat up in Alaska after I graduated from high school. And on the boat, we had a blast freezer that you could set the salmon in racks and roll it into this blast freezer and close the door, and it would freeze that salmon solid in 20 minutes, which is crazy. All right. And you did not want to be in there when the door closed, trust me. And so that's essentially when you oversize your equipment, that's what you're creating. You're creating a blast freezer. All right. And this blast freezer just blasts the cold air in. Your thermostat gets satisfied very quickly and the system shuts off. And then depending on how inefficient or efficient your house is, it raises back up again. Then it comes back on and then it shuts off. And then it comes back on and it shuts off. So that's short cycling, these short periods of time. It is much, much better for your air conditioner to run longer periods of time than it is to short cycle. Okay. Because imagine you're blowing really cold air into a room. There's a thermostat way over on the other side of the house, turning on the air conditioner. All this cold air is blowing into the room, and then suddenly it shuts off. What happens to that really cold air that you're blowing into this warm room? It's going to do its natural thing. It's going to sink down. So you start getting stratification. You start getting warm air rising and cold air falling. You get uneven temperatures throughout the house. Maybe this room never got to temperature like it wanted to, like the thermostat did. The thermostat was satisfied. The only happy place in the house is right in front of the thermostat. The only comfortable place in the house, typically. So there you go. Oversizing is not a good thing. Oh, one last thing, short cycling. Imagine driving your car where all you did was you stomped on the gas and then slammed on the brakes. Stomped on the gas, slammed on the brakes. Stomped on the gas, slammed on the brakes. How long would your car last if you drove it like that? Not very long. And the same thing applies to heating and cooling equipment. Okay. So lots of things. I have some amazing graphs. I did a whole bunch of data logger graphs of this neighborhood and showed how oversizing causes all kinds of problems. Okay. All right. All right, here we go. Brace yourselves. Super basic thermodynamics and the refrigeration cycle. Okay. So temperature is the measurement of the density of BTUs. Okay. That's not, there's scientists that'll go, that's not what it is. But essentially that's what it is. That's the easiest way to understand it. It's how dense are the BTUs in a volume of space. Okay. If you have a lot of BTUs in a house, it's going to be warmer. If you have fewer BTUs in the house, it's going to be cooler. Okay. So remember, temperature is essentially a measurement of the density of heat in a volume, in a space. Okay. And here's another thing. Everything has some BTUs in it. Everything has BTUs in it. Even a block of ice has some BTUs in it. Okay. The only place you can go where there's no heat or there's no BTUs at all is outer space. Okay. Absolute zero is out in outer space. So everything has BTUs in it. Heating is adding BTUs. We talked about that. Cooling is removing BTUs. You don't put coldness into something to cool it down. You remove the heat. All right. Here's a quiz question for you. You've got a glass of room temperature ice. Okay. Room temperature ice, room temperature water. You got a glass of room temperature water. You set it on the table and you put 2 cubes of ice into that glass. Did you add BTUs to that water? Is it going to get warmer or colder? Well, we know that the water is going to get colder. That's why we put ice in it, is to make it colder. Did we put coldness into that water, or did we add BTUs? We actually added BTUs. Those ice cubes have BTUs in them, and we put those into the water. So why did it get cold then? Well, it got cold because when we put the ice in there, you'll notice that the level of the water went up, right? The level of the water raised up. So now we have a bigger volume, and the ice that we put in there has much lower density BTUs. So we've lowered the average density of BTUs in the water. We've made it cold. Okay, we made it cooler. All right. So think of it. It's always about the BTUs. It's always about the BTUs. If you remove BTUs at the same rate, the temperature will remain constant. We talked about that. And then here's the other thing. BTUs are antisocial. Okay. If you've got a block of metal that's got a whole bunch of BTUs in it. They don't like each other. They're trying to get away from each other. And then you put it up against another block of metal that has fewer BTUs in it. All the BTUs are like, oh, let's get out of here. Let's go over there. There's less BTUs. And they'll all start going over there. But eventually there'll be the same number of BTUs over there. We call that equilibrium. So the two blocks of metal reach the same temperature, and then the heat stops moving. Okay. And so that's the second law of thermodynamics. And is that heat will go from a warmer place to a colder place. It's nature. It just does it automatically. All right. And we can take advantage of that. We can use that fact. It's like using gravity in our favor. We can use the fact that heat goes from a warmer place to a colder place. Okay. Very important concept. All right. Now here's another interesting thing. So if temperature is the density of BTUs in a volume, if we change the volume but leave the densities the same, the temperature also changes. Okay. The temperature also changes if we change the volume but don't change the number of BTUs, because it's about density, right? So let's say we got 9 BTUs in this container. All right. And we make the container bigger. Now the density is less, which means it gets colder. Then if we squash it down, the density gets small, the BTUs are more dense, have higher density, and it gets warmer. So we can change the temperature of something by changing its volume without changing the number of BTUs in it. Okay, another very important concept. A good example of this is, I don't know if you've ever watched or seen scuba tanks being filled with air. So a scuba tank is a very fixed volume of air, and they're cramming all this air into this thing, and the air is getting compressed, and that air has BTUs in it, and it's getting more and more compressed, and it starts to get really hot. And so they take that tank and they submerge it in water to take the BTUs away from it. Okay. Same concept. You're changing the volume without changing the BTUs. Okay. Oh, and then this works. You can actually do this with air. You expand it, it gets cooler. You compress it, it gets warmer. Okay. You can do that with air, but air is not that great. There's actually other types of gases that do this really, really well. When you expand them, they get really cold, and when you compress them, they get really hot. They actually change phase. They change from a gas to a liquid when you compress them, and that absorbs a lot of heat when it expands, and gives off a lot of heat when it compresses. Okay, those are called refrigerants. All right, you've heard of Freon and R22 and R12 and all the R410A and all the new crazy R32s and everything else. There's a big thing happening right now where they're replacing a bunch of refrigerants. But anyways, that's what a refrigerant is. It's a gas that does this very well. It changes temperature when you change its density. Okay. All right. So let's say we've got a space that is 70 degrees. And if we expand this container, it becomes 40 degrees, and we put it in the 70-degree space, what's going to happen? It's going to absorb BTUs. The BTUs on the outside are more dense, and they're going to say, oh, let's go inside where there's not as many of us. And they go inside the container. Okay. That's a natural way to move heat, is by creating a space that's colder than the BTUs around it, and they will go there. All right. It's like, I don't know, it's like putting sugar where there's ants. The ants will just come to it. All right. Then you can also squeeze it, and if it becomes hotter than the outside temperature, the BTUs leave. So it's just like a sponge. It's like a BTU sponge. It's a heat sponge. You expand the gas to absorb heat, and you compress the gas to give it off. And it's so the BTUs are going in and out, in and out, in and out, in and out, just by going up and down. Okay. All right. Now we take that concept, and this concept is very important. This is the whole key to the refrigeration cycle. All right. The fact that you can change the temperature of something by expanding it or compressing it, and the fact that if you can make it colder than the outside air, it will absorb heat. And if you make it hotter than the air, it'll give off heat. Okay. So that's exactly what the refrigeration cycle does. So now let's look at a house. And let's say it's 90 degrees outside and 70 degrees inside. It actually should be 75. Our indoor design temperature is 75, but let's just say somebody likes to set their air conditioner to 70. Okay. So all the BTUs are coming into the house. It's 90 degrees outside. All the BTUs are coming into the house. We need to remove those BTUs at the same rate that they're coming in order to keep it at 70 degrees. And we've got our little sponge. We got our little BTU sponge. We're going to test it out. All right. So we go inside the house where it's 70 degrees and heat is coming in. All right. We go inside the house where it's 70 degrees and we expand it to make it 40 degrees inside the container. We absorb some BTUs. All right. And then we run outside and squeeze them out. If we can squeeze it and make it 100 degrees, which is hotter than 90, all right, it's hotter than the outside temperature. So those BTUs are going to go out to the warm air. We're going to absorb them from the cool air by making the container colder than the cool air. And we're going to make them expel into the warm air by making them warmer than the hot air outside. Okay. But we would have to do that really fast. We got to run inside, expand it, wait for it to change temperature, run outside, squeeze them out, run back inside, expand it, run outside, squeeze them out. If we could do that fast enough, okay, we would be able to keep the house cool by doing that. But I don't think we would be able to do that. It would require a very large container with just the right refrigerant in it and stuff like that. And that would not be a fun way to spend your day on a hot day, would it? Running in inside and outside the house. Okay. So the point is that it's theoretically possible, right? It's theoretically possible. So, spoiler alert, we can actually go the opposite direction. If we can make the refrigerant colder than the outside air, we can absorb heat from the outside air, and then we can bring it in and squeeze it and make it hotter than the inside air, and then it'll jump out on the inside of the house. We can go the opposite direction. That's exactly what a heat pump is. A heat pump captures heat from the outside air by making the refrigerant colder than the outside air, and then it brings it inside, compresses that refrigerant, makes it warmer than the inside air so the heat comes out. So we can pump it in both directions. But the key is that the two ends get hotter than the outside, colder than the inside in the summertime, and then the opposite is true in the wintertime. Okay, so that's exactly what a refrigeration cycle is, except somebody got really smart, and instead of using these containers, okay, instead of using these containers, they said, I've got a better idea. What if we had a tube of refrigerant, and in one end of the tube, it was compressed, and in the other end of the tube, it expanded? Okay, that's exactly what an air conditioner is. It's a tube with refrigerant in it. Outside, we call this the condenser. There is a thing called a compressor, and it squeezes the refrigerant. The refrigerant gets very hot, and it gives its heat out to the hot outside air. If you have an air conditioner on your house, the next time it's running, let's say it's 90 degrees outside, and it's running, put your hand over the air conditioner and feel the air coming out. That air is hotter than the outside air. That's the heat. Those are the BTUs that used to be inside your house. They're being dumped outside by making this thing hotter than the outside air. So when the hot outside air goes by it takes away that heat. Okay. And then on the inside of the house, then this refrigerant, after the heat's been squeezed out of it, this refrigerant comes along and hits something called an orifice. And that's, just think of it as a spray valve. Okay. The refrigerant comes in as a liquid, it comes out the other side, and then it boils, and it absorbs heat when it boils. Okay. It's because the pressure is so much less, it's boiling, it's evaporating. And so we call that the evaporator. That gets really, really cold. And then when you blow the house air across it, it cools the house air. It removes the heat. All right. So that's the refrigeration cycle. There you go. That's the refrigeration cycle. Now, what if we want a heat pump? Do we have to take the condenser outside and the evaporator inside? We got to, in the spring and the fall, we got to swap them. We carry the big thing inside, we take the air handler outside. No, someone else was very, very smart. And they said, what if we just had a little valve that reversed the direction of the refrigerant? And we can do the same thing. So that's what a heat pump is. A heat pump is an air conditioner that runs backwards in the wintertime. Okay. All right. Let's see. We got our evaporators. The evaporator becomes a condenser, and the condenser becomes an evaporator is basically what it is. And so now we're extracting heat from the cold air and putting it into the warm house. All right. Okay. I do need to pick up the pace just a little bit. This is a good part here. So what exactly is a heat pump and why are they so darn efficient? Okay. So the alternative to electric heating from a heat pump, the alternative is electric resistance heating. Electric resistance heating has been around for a long time. If you have the old style electric stove with the coil tops on it, when you turn on the heat, it applies, you turn on the knob, it applies electricity, it starts to glow red. Turn on a blow dryer, you look inside a blow dryer, there's an orange wire that glows red. Anything where they apply electricity to it and it gets hot and gives off heat, that is electric resistance heat. Electric resistance is super efficient. Okay. It is so efficient that we basically call it 100% efficient. It's not exactly, but it's so close. We just say it's 100% efficient. But what is it efficient at? It's efficient at taking electricity and turning it into heat. Okay. So electricity has a certain BTU value to it. And if you take 5 units, 5 BTUs worth of electricity and convert it into 5 BTUs of heat, that's 100% efficient. You're taking 5 and you're getting 5. Okay. That's 100% efficient. That's really, really efficient. How much more efficient could you possibly be than 100% efficient? Okay. You hear people say, I give 110%. That's no such thing. You're giving, that means the rest of the time you're not giving 100%. Now you are giving 100%, right? So it's really efficient. So why don't we use electric resistance all the time? And the reason is those 5 little flying electric BTUs are very, very expensive. They're expensive. Okay. Gas, on the other hand, on a BTU per BTU basis, gas is roughly 1/3 the cost of electricity. So in order to compete with gas on a cost basis, we have to be 3 times more efficient than we use on gas. Gas furnaces have gotten really efficient. They're in the high 90s. They're in the mid to high 90s now, 94, 96% efficient. That's really efficient. Okay. And electric resistance simply can't compete, even though they're both 100% efficient. The stuff that we're using has a different cost. The electricity is way more expensive. So now to compete with gas on a cost basis, our 100% has to be 3 times more efficient than the gas to compete. So we have to be 300% efficient. How is that even possible? Okay. Well, it's possible if you cheat. Okay. Heat pumps cheat. They're cheating. They're not playing fair. They are not creating heat from the electricity. They're stealing the heat from the air that's already there. Okay. Now that's a harsh way to say it. You can say they're borrowing it if you want to, but they are taking electricity and using that electricity to steal the heat that's already there. Instead of creating heat, they're using it to capture heat that's already there. And it turns out you can do that for about 1/3 of the amount of electricity. I actually need to upgrade this slide. Now we're using 2 units of electricity and we're capturing 5 units of heat out of the air. Well, actually now we're capturing 6. It's closer to 6 now. And so if you're putting in 2 and getting out 6, what is that? That's 300% efficient. Yay, now we can compete with gas on a cost basis. Okay. That's why heat pumps are such a great thing, is they take electricity and they get the absolute maximum heating capacity out of it. The problem is, we'll talk more about this later. The problem is they don't do it quite as fast. Okay. It takes a little longer to do this. All right. But if we can deal with that, if we can handle that, it's worth it. It's worth it. Okay. All right. So, the advantages of heat pumps for space heating. Let's talk about that. I've got a question here. How does the cost of a heat pump for heating compare to gas heating? It depends. It depends. For new construction, heat pumps are cheaper to put in than gas furnaces. When I first started, after I graduated from college and I started doing energy consulting and stuff like that, this was in the late 80s. All the builders wanted to build all electric homes. Why? Because it was cheaper. But the energy code is based on cost effectiveness and said, you know what? It's actually cheaper to use gas. And so the energy code encouraged gas, and all the builders started building homes with gas. And now we're trying to get them to build all electric homes. And like, Well, okay, it's easier, it's cheaper to build electric homes. So yeah, okay, we can do that. All right. But the equipment itself is more expensive. All right. The equipment itself is more expensive for a heat pump than a gas furnace. So it just depends on if you're an existing home and you have a gas furnace, it's a lot cheaper to replace the gas furnace with a gas furnace. All right. But there's a lot of reasons to replace it with a heat pump, especially if people are throwing money at you and saying, here, take this money and swap it out with it. So that offsets some of that cost. Okay. And then there's a lot of other benefits of doing that. So let's talk about those benefits. So don't worry about the technology. Air conditioners, heat pumps are air conditioners that run backwards. Okay. Air conditioning has been around for a long, long time. The technology is there. The refrigerants have gotten really complex and really efficient. The compressors that squeeze the refrigerant have gotten super efficient. The motors, the fan motors, everything's improved over the years. Okay. And so the technology's there and it's working. Air conditioners move heat from the colder inside to the outside. We talked about that. They run backwards. One of the things I hear contractors say every now and then is, you know what, if you buy if you buy a heat pump, we'll give you a free air conditioner with that. How about that? That's a pretty good deal. It's the same thing. All right. It just runs backwards. A heat pump in cooling mode is exactly like an air conditioner that you would have on a furnace. It behaves exactly the same way. Okay. It's just when it kicks over into heating is when things get fancy, and that little three-way valve inside the condenser does its magic. Okay. Question here. Is there a reason not to add a heat pump to a home with a gas furnace instead of replacing a gas furnace so you can heat the home quickly and the heat pump can keep it warm? Yes, that is called a dual fuel system. Okay, dual fuel. There are certainly some cost advantages to doing that. A furnace is an air handler and it will work with a heat pump. The condenser outside is a heat pump and an air conditioner. It looks just like a normal one. And the coil, you can put that on the end of your furnace and it'll behave just like a regular air conditioner. So you can do what's called it's called an economic balance point. And when it's really cold, it's more cost effective to heat with a gas furnace. And when it's not so cold, it's much more cost effective to heat with the heat pump. And you can set your controls to flip back and forth. And then on really cold days, you've got that extra boost that you get up from the furnace. So yes, there's some really good reasons to do that. However, one of my personal reasons for getting rid of gas is safety. All right, so you have to take that into consideration too. Okay, and we'll get to
Russ,
that in a couple of
yeah,
slides. Yes.
I was that was a great. I was curious what you were going to say from a mechanical engineering standpoint on that
Yes.
question, but I did just want to add that most rebate programs, and I know some of them are offline right now, but they are only incentivizing folks who are taking out gas units. So just be aware of that. If you're going after the rebates and stuff like that, most of the programs are only designed for someone who's taking an existing gas unit and replacing it with a heat pump, but you can still do the dual system like Russ said if you don't care about rebates.
Yep. And look what just popped up. You want to handle that?
Oh, yeah. How loud is the heat pump? Does it make noise and disturb us and the neighbors? Yeah, we had this question come in. We've had this come in with our building department meetings before because a lot of cities and towns will have noise ordinances. And Russ, you kind of touched briefly on, how there's a condensing unit outside. It's very similar to an air conditioning, what you would see with a normal air conditioner, right? Whereas a gas furnace, everything is usually inside in a garage, that sort of thing. So, yeah, that is something to consider. There are, noise ordinances that are different depending on what city and town you live in Marin and anywhere in the Bay Area, frankly. And so it might be a problem if, you're in a neighborhood that has homes that are really close together, not a lot of yard space, and yeah, so that might be something that you run into an issue with this technology. There are also devices. And I don't we don't recommend any single manufacturer or company, but there's a company called Zombie Box, and they design boxes to go over generators. So obviously generators are very loud. But they are building, I think they have some models that are designed to go around condenser units to kind of muffle that sound And also, Russ, I don't know if you want to get into like the vibration and just making sure things are installed properly, because a lot of the times the noise comes from,
Like the rattling of the case
yeah, the
rattles and stuff like
rattling and
that.
stuff. So if it's not
Hmm.
installed with proper, those rubber gaskets and those things that, eliminate that vibration,
Hmm.
that can be an issue too. So.
Yeah. It is an issue. Manufacturers know about it, and that is one of the tests that they do on every condenser is they do a zone rating or a decibel rating, and you can look that up before you buy it. And some of them are much better than others in terms of the sound rating. So that's some research you're going to want to do, especially if you have any kind of sound ordinances in your area. They may require that you buy a much more expensive piece of equipment. But then there's also things you can do if you're just worried about like bothering you and it's your air conditioner and you're worried about or condenser and you're worried about bothering you. There's things you can do about that too, like what Kellen was saying. You can put plants around it and bushes around it and stuff like that. They are if you've ever been in a house when the air conditioner was running and you stood next to a condenser, it's loud. It's a big fan. It's a big fan moving. So you're going to have that same sound in the winter time that you will in the summertime. So that's definitely something you need to consider. So, okay. Let's see. We got a big long question in here. I'm installing a heat cool pump for the first time. We've never had AC, not used problem except for 5 or 6 nights a year. The house is 2,300 square feet. HVAC contractors suggested a 5-ton they can fit air conditioner with inverter variable speed technology. Your presentation has prompted me to question the need for a 5-ton. Good, I'm glad. And request a proposal for a smaller capacity. There are options 1.5 through 5. Yeah, there's even smaller ones than that. But I don't think you're going to need a smaller one than that. So what you need to do is ask the person bidding on the job to do a load calculation. Okay. It always, well, and then there's two things too, is because they are probably sizing it for the heating load. Okay. They're sizing the 5-ton heat pump for the heating load. And we'll talk about this in a few minutes, but sometimes when you size to the heating load, it's going to seem way too big for the cooling load. All right. But it's for the heating load. All right. So you have to look at both of those. And so the key is to do a load calculation on the house, heating and cooling load calculation, and then have them justify that 5-ton. The next size down is a 4-ton. There's no such thing as a 4.5-ton. Go to the 4-ton and say, why wouldn't a 4-ton work? And they might say, oh, it's because it won't meet the heating load. And that's a valid reason. Okay. So yeah, it's all about doing a load calculation. And then the other thing is airflow. Do a good duct design. I'm assuming this is a ducted system in your house. One of the things, sometimes you size your heat pump for your heating load and you just have to live with an oversized air conditioner. And I just spent 10 minutes explaining why that's a bad thing, right? Didn't I? And now I'm telling you, you're gonna have to deal with it. Well, one of the ways you deal with that is to have really good airflow, and that means properly sized ducts, big ducts that have a good circulation. And then the other thing is variable speed equipment, because variable speed equipment can act like a smaller piece of equipment. It can throttle down. So it can run full blast on heating mode and then run at half speed in the summertime because it's technically would be otherwise be oversized. So those sorts of things. Okay. All right. Hopefully that helps. So how cold can a heat pump be? Well, how cold can a heat pump work? What's the coldest freezer you've ever seen? What a chest freezer, a box freezer? What's the coldest freezer you've ever seen? I told you about the blast freezer on the boat. Um, that is the refrigeration cycle. It is a heat pump pumping heat from that compartment to the air outside of that compartment. And if it can work at that temperature, a heat pump, as long as the refrigerant can get colder than what the outdoor temperature is, it can work. I have a good friend in Minnesota who has heat pumps on his house and he's quite happy with them. Okay. I know people in Pennsylvania, I know people in Ohio, Michigan, all those very cold states, and they have heat pumps in them and they're working great. There's new heat pumps out there that are designed for colder temperatures. Okay. And they work great. And I say this all the time. If you could pick a climate in the country that was perfect for heat pumps, it would be the Bay Area. Okay. It's perfect. Mild summers, mild winters. You couldn't ask for a better climate to put a heat pump. Okay. All right. They're being successfully installed in all the regions of the world. The Bay Area is an ideal climate. You can put electric resistance on there as a supplementary heat for those really, really cold days where you just need that little extra boost, or for emergency backup. Okay. One of the downsides of the heat pumps is they're very complex. There's more moving parts to potentially break down. And so if that compressor gives out, you can have electric backup heat. You don't want to do it for very long because it'll be expensive, but if it's not running all the time, it's not that big of a deal. Okay. All right. And then here's my thing. I'll try not to get up on my soapbox too much. I'm a mechanical engineer. I design heating and cooling systems, and it's never sat well with me to design a system. I design subdivisions and all this other stuff. To design a system where you're piping explosive gas into these people's homes. When you use that gas, it turns into a poisonous gas. And if anything goes wrong, it goes wrong really badly. Okay. And I've had situations in homes that I designed where bad things happen. It wasn't my fault, but it happened, and I felt bad. I felt bad, but it was the builder told me to put in that kind of system. I didn't force them to put in a gas furnace. But just go on YouTube and Google and search for exploding house, and there's dozens of videos of houses blowing up. Okay, we had one in Sacramento at Christmas, and you guys all know about the stuff in the Bay Area, but so heat pumps don't have all those problems. There's no explosive gas, there's no carbon monoxide, and there's no open flame. If you have an older furnace in your garage and you store gas cans on the other side of the garage, that those fumes can come down. And that's why water heaters and furnaces have to be up off the ground so they don't ignite that gas. Okay. When you open a furnace and you look inside the furnace, you're going to see wires and tubes and sensors and buttons and all this other stuff. Those are all safety devices. Those are all safety features. Okay. When you open a heat pump fan coil unit, you'll see a fan, a coil, and some wires, and that's it. It looks empty compared to a furnace because they don't need all that stuff, all those safety devices. This is a quote from a building official, from a building department. He said, the potential for something to go very, very wrong with a gas furnace is much higher than people realize. This is why CO detectors are required when you do anything to your house, including add a sink. So if you've ever gotten a building permit to do something like replace a toilet and a sink in a bathroom, remodeling a bathroom, you might remember that one of the things they require is that you put carbon monoxide detectors in your house. What does that have to do with the sink? Okay, it has nothing to do with the sink. It has everything to do with the fact that everybody needs a carbon monoxide detector if they have any kind of burning gas in their house. I've been certified. I was a proctor. There's an organization called BPI, Building Performance Institute, and I'm running over time. My goodness, I'm sorry. The more I learned, I was like, how in the world have we survived this long? We've been very lucky. Okay. So anyways, again, I'm sorry. I said I wouldn't get on my soapbox, but I did. I apologize. But that's my personal reason for wanting to get gas out of our house is for the safety part of it.
Russ,
It's cleaner. Oh yeah.
I encourage folks to just type in questions because we've been answering them as we go along. So yeah, I think we're doing all right on time. Just let you know.
Okay. Okay, cool. Let's see. Prices. Oh man. Prices have shot up recently, and to replace I don't know, Kellen, you might have more information if you've been looking at some of the applications and stuff like that, but it's not cheap. And it's gone up a lot lately. Let's see. 20 years ago, friends put in a heat pump in their house. It worked well. I wanted to do the same here in Mill Valley, but had to put in a gas heater because the contractor said the heat pump won't work. Yes, because there's not a significant difference in temperatures. Interesting, inside and outside. I didn't believe him, but we put in a gas furnace. The heat pump has improved a lot, and what they told you was wrong. The having a lower temperature difference between inside and outside heat pumps will actually work fine. I think what he may have been saying is that the air that it blows out of the registers isn't as warm as what you might be used to with a gas furnace. It doesn't heat the air up as much. Okay. And if that air that's not as warm, it blows on you, it could, and it's below your body temperature, it might actually feel cool. So that's one of the big complaints is that people are, oh, it blows cold air. Well, no, it's not blowing cold air. It's just blowing air that's lower than your body temperature, so it feels cold. But if you're trying to keep your house at 70 degrees, you can theoretically heat your house with 71-degree air. So you're going to take a lot more of it. All right. But heat pumps, they blow, 90, 95-degree air. Okay. Whereas a furnace will blow 120-degree air. And if that's what you're used to, it's going to seem different. All right. But it will keep your house comfortable. It will keep your house warm. Live on the Marin Coast, 100-year-old house. Oops. Walls are uninsulated. Windows are single pane and leaky. We are hardy, but winters are cold and damp. Summers are not a problem. Use electric wood heat. Yeah. The first thing I would suggest is improve the house. Okay. There's ways to insulate walls. You can drill holes and blow insulation in them. You don't have to replace your windows. They make window storm windows and things like that. But if you think about it, replacing windows it's not cost effective. It will increase the value of the house. One of the things I hear the most is when people replace their windows is it's much quieter in their house. The ceiling, what we call the ceiling membrane, the sheetrock in your ceiling, that leaks like crazy. All right. And if you have a little bit of dirty insulation on top of that, you're better off sucking that all out. Hire a contractor that will remove the old insulation and then seal the membrane at the top, seal it really good, and then put new insulation in on top of that. A lot of things you can do to improve that. Okay. And then a much smaller heating system. Well, you'll use a lot less wood, okay, a lot less electricity. And for your space, you might have baseboard heaters or plug-in wall heaters and stuff like that. So it reduced the load before increasing the capacity. Okay. Advantages, they're simpler, they're cleaner, they're cheaper to install. There's no gas pipe, there's no flue vents, there's no combustion air vents. They're lower maintenance. Okay. A heat pump is lower maintenance than a furnace. The problem is people don't maintain their furnaces like they should. They should have people out there at least every other year looking at your furnace. Okay. The burner ports get dirty. The condensate, if it's a high efficiency to have a condensate drain, you can get, just all kinds of stuff can go wrong. Now for heat pump water heaters, this is not necessarily as true as it is for heat pump space heaters. Heat pump water heaters have a filter, an air filter that you have to change. Okay. And so that does require pretty constant maintenance, but heat pumps require much less maintenance than a gas furnace. And now they come in really small sizes. You guys have probably heard of ADUs, an accessory dwelling unit. Okay. Houses are getting much more efficient. ADU houses are getting smaller and more efficient. And it used to be the smallest heat pump you could buy was 1.5 tons, 18,000 BTUs. Well, what if you build a small house and the load of that house is only 8,000 BTUs? Then the smallest heat pump you can buy is way too big. But now they've got smaller ones. Heat pumps are now, you've heard of ducted mini splits, ductless mini splits. Okay. Mini splits. They're getting all the way down. If you shop around, you can buy one that's 6,000 BTU capacity, half a ton. Most of the manufacturers, the smallest they make is 9,000 BTUs, 3/4 of a ton. Then you got 1 ton, and then you get up to the 1.5, and then they get up to the bigger ones. Okay. So now the equipment is more properly sized for these small houses and for these really super efficient normal size houses. You've heard of passive house and stuff like that. They're getting these big houses down to a little teeny tiny load by making the house super efficient. And so the smaller sizes equipment work better. And then they're cleaner, no carbon emissions. If you have solar panels on your roof, it's kind of a no-brainer to get rid of a gas furnace. You own your own electric company. You own your own power plant. Why are you paying the gas company for something that you could provide for yourself for free? Okay. So that's what you really need to do. Okay. They're really efficient. We talked about that, 300+% efficient. And now they are cost effective. They are neck and neck with gas furnaces in most places. It all depends on the time of use rates and all this. It's complicated. But now we can compete. We're no longer 3 times more expensive than it used to be. Now we're neck and neck with gas. So they've taken away the vast majority of the cost reasons for not switching to heat pumps. Okay. Some disadvantages. Let's be fair. Let's talk about the bad stuff too. Okay. The equipment is much more complicated. The controls, and cars were the same way. Cars used to be really simple. Now a car is a computer with wheels. And the technicians who work on those had to change with the cars. The same thing's going to happen with heat pumps. Okay. Technicians are going to have to keep up. And there's always a lag. There's always be a time when it's going to be hard to find someone who's qualified. The controls are more complicated. All right. More so on heat pump water heaters than on heat pump space heaters. But it's cool that you can control them with your phone and stuff like that. But they are more complicated. They can be more difficult to operate by homeowners. There's other settings you may not be used to, like the setting that the resistance strip lockout setting and things like that you might not be used to. They can, here's my big thing about heat pumps. They can be impacted by bad design and installation. Okay. A gas furnace is a dumb beast. You just turn it on, there's flame inside of it, gives off heat. Okay. It's hard to mess that up. Okay. But heat pumps, if you don't size it correctly for the load, if you don't have good airflow, if you don't have good refrigerant charge, it won't work as well. All right. All the benefits that you were hoping for can be blown out the door by doing that. So that includes oversizing, that includes undersizing, that includes undersizing the ductwork and things like that. Okay. So designers have to be much more careful with load calculations. But here's the deal. Contractors have always been required to do load calculation. That's been in the code for I can't tell you how many code cycles, but they just haven't been doing it. And now it's time to hold their feet to the fire and say, look, contractors, you need to start doing this stuff. You need to start doing what you're supposed to do, and that is to do a load calc on a house and size the equipment correctly. You've been getting away without doing it for far too long. All right. Question here. Sorry if this is redundant. Ducting to various zones. How is that accomplished? Well, you do what's called a room by room load calculation. Okay, so we do a load calculation on a house. There's two kinds. There's what's called a block load, which is the entire house. You can use that to size your equipment, but if you're going to do ducts, you need to know where that air needs to go. So you do what's called a room by room load calculation. So you know the load of each individual room. And if this room happens to be 10% of the total load, it's going to get 10% of the airflow. So when you pick your equipment, you know how much air you want it to move, and then you distribute that air accordingly. And if you know how much air needs to go to each room, you know how big the ducts need to be. Okay. The process for doing that is called manual J load calculations, manual S equipment selection, and manual D duct design, JSD. Okay. And that's a whole process of doing that. And then you get nice, really even temperature distribution in all the rooms when you do that. Okay, if a contractor, this was funny, you had this example a minute ago. Somebody asked this question or mentioned this. If the contractor tries to talk you out of getting a heat pump, find another contractor. Okay, that is a really old, outdated attitude to have, and it was because they didn't size them correctly, and they got a bunch of complaints, and they said, you know what, I'm never going to install one of these things again because they were doing it wrong. Okay, it's not the heat pump's fault; it's the designer's fault. All right. Grid reliability issues. We're switching from gas to electric for our heating. Isn't that going to put a big burden on the grid? And the answer is possibly, but the grid is improving. Okay, the grid is getting better every day. And so if you're going to put a HVAC system in your house, it's going to be there for a long time, 15, 20 years probably. Okay, or longer even. And at some point in that time, you're going to wish you would have put in electric. All right. So if you put it in now and be an early adopter, although it's too late to call ourselves an early adopter now, it'll pay for itself. Okay. It eventually, the grid reliability issues will be resolved and it won't be a problem. All right. And then the other issue that we run into a lot is if you want to switch to a heat pump, it might require that you upgrade your electric panel. All right. But there are some really cool technologies that allow you to share circuits and you don't have to upgrade your panel. So you just have to have someone come out and evaluate it. All right. So there's a whole bunch of advantages and there's some disadvantages. The thing about the disadvantages, if you look at them closely, they're all avoidable. Like being susceptible to bad design is avoidable by doing a good design. Okay, they're manageable. We can deal with that. And we just have to get used to it, the controls and stuff like that. And they're all improving over time. They're just going to get better the farther along we go. Okay. All right, let's talk about the different types of heat pumps. So the good old fashioned heat pump, the very first house my wife and I bought after we got married in 1990, had a heat pump in it. And it looked very similar to what you see here. It was just looked like a plain old air conditioner. But when you go up in the attic, it wasn't a furnace, it was a fan coil unit. Okay. And it worked fine. We had no issues with it. This was back in 1990. So they've been around for a long time. So you've got a condenser. You've got a fan coil unit that's got a big fan, a big squirrel cage fan inside of it. And then inside here is something called a coil. It's an evaporator coil. It looks like a radiator on your car, but it's shaped like an A, and the air blows through it. It's got all the aluminum fins and everything. The air blows through it and it cools the air. And excuse me. And they're connected by refrigerant lines. Okay. There's a larger one about the size of your thumb. It's a copper line. It's called the vapor line or the gas line or the suction line, different names for it. And that's the one with the insulation around it. And then there's a smaller one about the size of your pinky that has the liquid refrigerant going through it. So it goes out, it goes up into the house as a liquid, and it comes back as a gas, and goes like that. Okay. Now we've got mini splits, and you'll start seeing these, what we call a suitcase condenser. It's shaped like a suitcase with the fan on the side instead of on the top. Okay. And so they're smaller. They come in much smaller sizes. And there's different kinds. And then what most people think of when you say mini split is they think of a ductless mini split. Okay, so I like to throw this out there first. They make ducted mini splits. So instead of the cassette that hangs on your wall or mounts in your ceiling, it's a little box with a fan in it. You can hook ducts up to it and run the ducts out to the different rooms and get good distribution. Okay, so this is a single head ducted mini split. Okay, you can also get multi-head mini split. So it's one condenser that serves multiple indoor units that we call heads. Okay. So you can have one-to-one or you can have multi. The heads can either be ducted or ductless, and you can mix and match even. It's kind of interesting. And you can have, for the ductless, you can have the wall cassettes like this. Those are very common. Or you can have these ceiling mounted cassettes like this. So there's a lot of choices, a lot of options that you can do. Okay. So a lot of neat stuff out there. Do your research, look into it, make sure that the contractor does a good load calculation on the house. All right. And takes their time in designing your system. All right. Typical heat pumps that most of the ones we talk about are air source heat pumps. That means they get their heat from the air. There are other places to steal those BTUs from. Okay. You can steal those BTUs from water. If you live next to a lake or a stream, you can steal those BTUs from the ground. The problem is that you need a big space to do that. If you've ever seen pictures or maybe seen a neighbor doing it, they dig a huge trench and they lay that coiled black pipe down in the bottom of it and they backfill it with dirt. That's, instead of capturing BTUs from the air, it's capturing BTUs from the ground. The ground has a lot of BTUs in it. All right. So that's called a water source and a geothermal heat pumps. So those are options. All right. Sizing heat pumps. Because heat pumps provide both heating and cooling from the same unit, you don't have as much flexibility. If you have a gas system, you can pick a certain size furnace to handle your heating load, and you can pick a certain size air conditioner to handle your cooling load, and then put those together, and they'll be sort of custom to your heating and cooling loads. You don't get that with heat pumps. So you have to be more conscientious. You have to be more deliberate about how you size your heat pumps. Okay. But they can work just fine if you do a good design, they'll work just fine. So you have to kind of choose. In the Bay Area, you're probably going to lean towards heating. Okay. And you're gonna say, let's size it to the heating. And then let's take what we get for cooling and compare that to our load. And typically what you'll find is it's oversized for cooling. All right. But that's not a problem if you have good duct design and you have variable speed equipment. And the fact that, as somebody mentioned, you hardly run your air conditioners. It's not like over here where it's towards the Central Valley, the Sacramento Delta area where I live. It gets really hot. You turn your air conditioner on, it runs all day. And if it's oversized and you're running it that often, you're gonna notice problems. But if you're only turning your air conditioner on for those 10, 12, 14 days a year that gets really hot, it's actually nice to have a big air conditioner, and you just like, wow, it cools faster, right? It's sort of an on demand, but don't get complacent about that. You should not run your air conditioner like you treat your air conditioner in your car. You just get in and you turn it off full blast. Okay. That's not how you want you ideally you want to set your air conditioner and then just forget about it like you do your refrigerator. Do you adjust the temperature on your refrigerator? No, usually. And so you just set it and forget it. Okay. That's how you should run it. But in your guys' climate, it's a kind of unique situation. You only turn your air conditioner on when you really, really need it. Okay. Out here in the Central Valley, Sacramento area, we turn the air conditioners on in May and then leave them on until October. Okay. All right. So here's the thing I mentioned earlier. Be sure to use a qualified licensed contractor that understands the design process. Manual J, Manual S, Manual D. Manual J is load calculations. How much heating and cooling does your house need? Manual S is picking a piece of equipment that's appropriate for that load. And then Manual D is designing the ducts to get good airflow and good distribution. There is a new version of Manual J that just recently came out that spends a lot more time on heat pumps. There's a lot more options for how to properly size a heat pump than there used to be. Most designers would size the heat pump for the cooling capacity. And then if it was short on the heating side, they would make it up with heat strips. Okay. But now because of the improved technology, you can size your heat pump to handle your heating load and then make sure there's no issues associated with oversizing the air conditioners. There could be a situation where you size it to the heating load and it's just way oversized for the cooling load. So you go down a size and then you say, okay, I may not quite meet my heating load, but remember I said Manual J is safe. You can go ahead and put electric strips backups on there. They'll probably never run. Okay. They'll probably never run. But that's another, just that's the sort of thought process that has to go through. Heat pumps are working fine all over the state. Even in Tahoe, Truckee, there's heat pumps up there that are working fine. Okay. The general recommendation today is to size the heat pump for the larger of the heating or cooling load, even though it might be oversized for the other one. And then what you do to resolve those issues is have good duct design and variable capacity or two-stage heat pumps. Okay. All right. As long as your heat pump heating capacity is properly sized to handle the heat load without strips, the heat strips should never come on, but they can still be there as backup heat. I work with a lot of contractors in Florida. Okay, we sell design software, and a lot of our customers are out in Florida. So I'm always talking to contractors out in Florida. They don't have gas in most parts of Florida. They don't have gas. So everything's electric out there, and they've been using heat pumps in their homes for a long time. But of course, it's Florida; it doesn't get cold. But it's funny they will size their heat pump for the air conditioner, and then it may not quite meet the heating load. They'll put heat strips in there, and after a while, they're just like, you know what? I put heat strips in, but I don't hook them up. That's what they tell me. I put heat strips in these houses. I don't even hook it up. But if the homeowner does complain and the winter rolls around and they're not comfortable, I just go out there and just plug it in, and then they're good to go. And what they're finding is they hardly ever run the heat strips because Manual J is safe. Okay. Heating setbacks, you generally don't need those for heat pumps. Set up, set back, or you like it to be colder at night when you're sleeping. You can do that, but you don't need to do that to save energy like you would with a furnace. Okay. When it goes from that colder temperature and it kicks up to that warmer temperature in the morning when you get up, that change in temperature can make the backup strips come on if you're not careful. So you need to be careful about that. Let's see. One of the most common problems with heat pumps is they just don't understand the controls. Okay. All right. Well, we have
You got it right in there.
2 minutes, 2 minutes for Q&A. Sorry about that. I know you guys were great about putting stuff. Oh, I missed one. There's a heat pump water heater that uses CO2. Yes, the Sandin units. High efficiency will HVAC heat pumps start using CO2. I think there are some out there that have. They are quite expensive though. But it is, yeah, as far as refrigerants go, that's about the safest refrigerant you're going to get. Yeah. But yeah.
There's a couple that came in the chat.
Oh.
What about radiant heating, like Eichlers? I don't know if you want to touch on the radiant at all.
Oh, so radiant floors, if you're going to do a radiant floor, you would use a heat pump water heater, but I would have a separate water heater for the space heating than for the um, space heating versus domestic hot water. Okay. You don't want to do what's called combined hydronic, where the same water heater is providing um, domestic hot water for showers and bathing and stuff and providing space heating. You're asking for trouble. I'm sure there's some out there that are big enough to do that, but the problem is now they're fighting each other. And if you have company over, for Christmas, family over, staying over, take a bunch of showers, you run out of water. Well, now not only are you taking a cold shower, but you get out of the shower into a cold house. So you can do it, but I would recommend separate water heaters.
Okay. There's one from Dan that says, wonder about our thermostat. We set it at 70 and the heat pump keeps running to 74. What's going on?
You set it at 70, it's running to 74. And I assume that means in the summertime. So it's over conditioning. Is it one of those multi-head systems, or is it one-to-one? Can you type in the chat? Is it a multi-head heat pump systems? They are running into problems with those because if it's multi-heads on one condenser, when one is calling for heating or cooling, they all have to run at the same time. They don't stay off. A lot of people think they shut off. They don't. And so if this one over here is oversized for the space and this one over here is properly sized, the properly sized one is going to run when it needs to, but every time it turns on, that other one has to run on low speed. And that could overheat that space. I've heard that be a common complaint. Other than that, the only thing I can think of is in your thermostat settings, there's something called a dead band, which is the difference between the temperature where it turns the heater on and the temperature it turns the heater off. And you can set that range. And so if that range accidentally got set too high, it might be getting much higher than you want it to be before it shuts off. That's the only other thing I can think of.
Okay. And then I guess I can take this one. So if the power goes out, the heat pump will stop working. Correct. These all run on electricity unless you have battery backup, perhaps a generator. I will point out that a central furnace that uses a fan to, pump the air through the house, that's not going to work either.
It'll stop
Yeah.
working as well. Yeah.
Okay, well, we are at 2 minutes over, so thank you so much, Russ. Oh, there's Sarah. Sarah, do you want to talk about Electrify Marin? So yeah, there were some questions earlier about the rebates. I kind of just wanted to skip all that and stay with the technology because we're going to send out information on the current rebate programs and how to access those, in the email that follows up. But the county does have a program, and Sarah Thatcher is our new program coordinator for Electrify. Sarah, do you want to go ahead and introduce yourself?
Yeah, really quickly, I'll just say hi. I just threw in the link to our the page on our website where you can find out more information, and my contact information is there as well if you want to reach out with any questions. But yes, we have our rebate program active, and that applies to replacing gas or propane appliance with a heat pump, water heater, heat pump, space heater, or induction cooking appliance, or a mini split heat pump as well in there. And yeah, I'm available to answer any questions, and it's very clearly laid out on that website, the step-by-step process for submitting the application. But make sure you look into that before you actually move forward with the installation so that you're clear and understand what our process and what our efficiency requirements are in there too.
Great. Yeah, the question came in, is the Electrified Marin part of the IRA? No, so this is the county's own program, which is great because it doesn't matter what the executive branch says. We can do what we want over here. We also make it available to propane. That's not something that is available to some of the utility programs. So we've definitely tailored it to Marin. And we're also contractor agnostic because we've noticed that could be an issue. So we don't care who you use, you just have to get a building permit. Most of the other programs, they require contractors to enroll in their program in order to offer the rebate. Okay, well, we are definitely over, so I'm gonna cut it off just to respect everyone's time. Thank you so much for spending an hour and a half with us this evening. Again, I'm going to be sending out the recording once we get that uploaded and the slides, and I'll have links to our survey and website and everything. So once again, Russ, thank you so much
My pleasure.
for spending your time with us, and we will see everyone next time. Have a good night.